Hello everyone. In this tutorial, let's go over this question on FSM, Finite State Machine. So the question is, a synchronous sequential circuit has one input and one output. The output becomes 1 if the circuit detects a sequence of 0, 0, 1, 1, 1. Otherwise, it's 0. So in part 1, we're asked to make the state diagram and state transition table. In part 2, we're asked to design the circuit using D flip-flops. So before we get started, let's have some background. So we need to detect 0, 0, and we're going to use Mealy machine, by the way. In Mealy machine, the output is a function of the state and the input. In Moore machine, the output is a function of the state only. So we need to detect 0, 0, 1, 1, 1. So 0, 0, 1, 1, 1. When we detect this sequence, the output will be 1. Otherwise, it will be 0. So that means we have 5 states. How many bits we need to store in each state? So in part 2, we need to know how many D flip-flops we need. Each one D flip-flop can store 1 bit, either 0 or 1. So what is the least number of D flip-flops we need? So we already saw that in previous video. We can do log 2, the number of states. And the number of states is 5, because we have here 0, 0, 1, 1, 1. So if we do the math here, this will be 2.32. So that means we need 3 flip-flops. And we need 3 bits in each state. Another way to see this, let's say we have 1 flip-flop. We're going to use 1 flip-flop. So we do 2 to the power 1. So this is 2 states, which is not enough. Let's say we're going to use 2 flip-flops. So this is 2 to the power 2 will give us 4 states. Also is not enough because we need 5 states. So 3 flip-flops. This will give us 2 to the power 3 will be 8 states. So this is enough. So we use 5 and 3 states remain unused. So now let's get right into it. So as we mentioned, we have 5 states. So let's call them S0, S1, S2, S3, and S4. That's 5 states. So let's assign the 3 bits for S0, 0, 0, 0, for S1, 0, 0, 1, for S2, 0, 1, 0, for S3, 0, 1, 1, and then for S4, 1, 0, 0. So let's start with part 1. So we have S0, we have S1, we have S2, S3, and S4. Now let's see how we transition. So first, let's assume we are entering the right bits, the correct bits, 0, 0, 1, 1, 1. We are not making any mistakes. So if we enter 0 at S0, we can only go to S1. So the input is 0, the output will be 0. At S1, if we enter another 0, we go to S2, the input is 0, the output is 0. At S2, if we enter 1, so 0, 0, and we have 1, so we go to S3, the input is 1, the output is 0. At S3, we have 0, 0, 1, and then we enter another 1, we go to S4, that's 1, the output is 0. Now we have 0, 0, 1, 1, if we enter another 1, we go back to S0. So that's the input is 1, and then the output is 1, because we completed the sequence. So here we have, at S1, we enter the first 0. At S2, we enter the second 0, 0, 0. At S3, we entered 1 bit, so that's 0, 0, 1. At S4, we entered another 1, so that's 0, 0, 1, 1. And then from S4, we entered another 1, so that completed our sequence, 0, 0, 1, 1, 1. The output is 1, and then we started over. So now let's see if we are at S0, and then we enter 1 instead of 0. So we have only one option, to remain at S0 and start over. So here we entered 1 accidentally, the output will be 0. Now we are at S1, we have 0. We're supposed to enter 0. Let's say we entered 1. So we have two options. We can remain at S1, or we can go back to S0. The way we look at it, we have 0, 1. If we stay at S1, can we make the correction and continue the correct sequence? No, because we started 0, 1, at S1, so we have 0, 0, 1, 1, 1. So that means we need to discard everything and go back to S0. So that's if we entered 1, the output will be 0. Now we are at S2, we have 0, 0, we're supposed to enter 1. Let's say we entered 0 accidentally. So we have a couple options. We can remain at S2, we can go back to S1, or we can go back to S0. So what do? Can we make correction? Yes, we can discard 1, 0, so we'll be left with 2 zeros. In this case, we have to remain at S2. So we remain at S2, we entered 0, and then the output will be 0. So now we discard 1, 0, we have 0, 0, we can make the correction and continue. Now let's say we are at S3, we have 0, 0, 1, we're supposed to enter 1, but let's say we entered 0 accidentally. Also, we have a couple options from S3. We can remain at S3, we can go back to S2, we can go back to S1, we can go back to S0. What do? So let's see this sequence. We have 0, 0, 1, 0. So let's see what can we discard in the back here. If we discard 1, 0 here, we'll remain with 0, 1, 0. That doesn't correct our sequence. If we discard 0, 0, we'll be remaining with 1, 0. We cannot continue the correct sequence. So that means we need to discard all of these 3 and go back to S1. So we'll be left with 1, 0. So that means we can continue from S1 and still make the correct sequence, 0, 0, 1, 1, 1. So this is how I see it. So at S3, if we enter 0, we go back to S1. We entered 0, the output will be 0. I hope this is clear. So now at S4, we have 0, 0, 1, 1. We are supposed to enter 1, but let's say accidentally we entered 0. Where do we go? We have a couple options. We can stay at S4 and discard this 0, discard 1 bit, this 0 here in the back. We can go back to S3, discard 2 bits. We can go back to S2, we can go back to S1, or we can go back to S0. So what do? If we discard this bit here, so we cannot make the sequence right because we need 2 zeros. If we discard 2 bits, we cannot make it correct. So that means we have to discard all of these 4 bits and keep the 0 so we can continue the sequence. So that means 0 takes us from S0 to S1. So that means if we enter 0 at S4, we go back to S1. Let me use another color for this. So at S4, if we enter 0, we go back to S1. The input is 0, the output is 0. So this is our state diagram. We completed first part of part 1. So the next question is to make the state transition table. So let's clean the state diagram a little bit. We didn't need this. We just used them to kind of explain the state, how we do the state transition. That's all we need. This is our state diagram. So next part, we need to make the transition table. So let's write it here. In the state transition table, so we have the current state, and then we have the next state. So we said each state is a 3 bits. So let's give them some generic names. So let's say this is a Q3, Q2, and Q1. Then because we're using Mealy machine, the output is a function of the state and the input. The input is X. So this is our input. And then we want to figure out what will be the next state. So let's call them Q3 plus, Q2 plus, Q1 plus. And then we want to figure out what will be the output. So let's call the output Z. So this is the output. So let's start with all possible current states. So we have S0 is 0, 0, 0. The input at this state, we could enter 0 or we could enter 1. So that means we need to write it twice. So this is S0. Next, S1 is 0, 0, 1. Same idea. We write it twice because we want to see what happens if we enter 0 and what happens if we enter 1. So this is S1. So similarly for S2 and S3 and S4, S2 is 0, 1, 0. So now we want to figure out the next state. So let's say we are at S0 and then we enter an input of 0. So this takes us to S1. S1 is 0, 0, 1. So this will be the next state 0, 0, 1. and the output is 0. We are at S0 and then we enter an input of 1, so we remain at S0. So the next state will be S0, which is 0, 0, 0, the output is 0. Now we are at S1 in the third row and we enter 0. S1 we enter 0, we go to S2. S2 is 0, 1, 0, so 0, 1, 0, the output is 0. We are at S4 and we enter an input of 1, so this takes us back to S0 and the output will be 1 because we completed the sequence as we can see here. So S0, 0, 0, 0, and the output is 1. So at this point we completed part 1. Part 1 we made the state diagram shown here and we made the state transition table. So in part 2 we need to design the circuit using D flip-flops. So we're going to do this, we're going to use K-maps to get the minimal Boolean expression for each input of the flip-flops. We're going to call them D3, D2, D1, but we'll do this in a separate video, part 2. Stay tuned for part 2. Thanks for watching. I hope this was helpful.